Welcome to the Explainer. I am absolutely thrilled to have you here today because we're about to go on a seriously fascinating journey. We're going to start way down in the invisible world of quantum physics, looking at the actual atomic structure of matter. And then we're going to trace those microscopic principles all the way up to that very real, incredibly compact power charger that is probably sitting on your desk right now. I mean, have you noticed how the power bricks for your laptops and phones have suddenly become like half the size they used to be? Yet somehow they charge your devices faster than ever? It feels like magic, honestly, but it's actually a total triumph of solid-state physics. Okay, let's dive into this and totally demystify the abstract physics powering your increasingly fast and tiny electronic devices. So here's our roadmap for today. First, the physics of energy bands. Then, electrons and phantom holes. Third, the wide bandgap revolution. Fourth, silicon versus gallium nitride. And finally, the global energy impact. I promise you, the heavy microscopic physics we start with is going to have a massive real-world payoff by the end of this. All right, section 1, the physics of energy bands. To really understand modern power chargers, we can't just look at the plastic casing or the plug. We first have to understand what makes a semiconductor tick at the fundamental atomic level. So, in crystalline materials, electrons don't just exist anywhere they want. They occupy these closely spaced energy levels that form what we call bands. Because of the Pauli exclusion principle, electrons can't share the exact same energy state, so these bands represent the allowed neighborhoods for electrons. Now, think of moving an electron to a higher, empty energy band so it can conduct electricity, kind of like jumping over a hurdle. In metals, the bands are half-filled or overlapping, so there's literally no hurdle at all. Electricity just flows effortlessly. In insulators, that hurdle, which is the forbidden energy gap, is a massive, completely impossible leap. But in semiconductors, there's a small band gap between the filled valence band and the empty conduction band. The hurdle is there, sure, but with just a tiny bit of energy, an electron can easily jump over it. And that delicate balance, that is the entire foundation of modern electronics. Now, to actually calculate where these specific hurdles are, physicists use something called the Kronig-Penney model. And look, I'll admit, this involves some incredibly heavy transcendental math. It basically simplifies a super complex three-dimensional crystal lattice into an infinite series of one-dimensional rectangular potential barriers. Think of it as a repeating track of hurdles. By solving Schrödinger's equation for this periodic potential, we get the mathematical proof for our bands. But hey, don't worry about the complex equations. The absolute crucial takeaway here is simply the creation of these allowed and forbidden energy zones. This model proves mathematically that electrons in a crystal can only exist in specific energy bands, separated by gaps where they absolutely, under no circumstances, can exist. Moving on to section 2, electrons and phantom holes. Now that we know exactly where electrons can and cannot be, we're about to look at one of the most fascinating optical illusions in all of solid-state physics. When an electron jumps over that bandgap hurdle into the conduction band, it leaves behind an empty space in the previously full valence band. We call this empty space a hole. Now, a hole isn't a real physical particle, but mathematically and physically, it behaves exactly like a positively charged particle moving through the crystal. It's kind of like a packed parking lot, right? If one car moves, it leaves an empty space. As other cars shuffle around to fill that space, the empty space itself appears to move across the parking lot. In solid-state physics, it is so much easier to keep track of that one moving phantom empty space than it is to try and calculate the individual movements of the millions of surrounding cars. But there's another quirk here. When these electrons and holes move, they aren't moving through a perfectly empty vacuum. They're navigating through a dense forest of atoms, that periodic potential we just talked about. Because these atoms get in the way, the electrons don't accelerate quite the way Isaac Newton would expect them to. But instead of throwing out the fundamental laws of physics, physicists just, mathematically tweak the mass of the electron to make the equations work. We call this the effective mass. It's a brilliantly practical workaround that accounts for the drag of the crystal lattice. And these carefully calculated band gaps, they aren't static. They're actually highly sensitive to their environment. For example, if the temperature increases, the extra thermal energy causes the atoms in the crystal to vibrate more, which increases the interatomic spacing. This actually causes the energy band gap to shrink. Plus, if we heavily dope the semiconductor, meaning we intentionally add a massive amount of physical impurities, the wave functions start to overlap, which also shrinks the band gap. And this brilliantly illustrates how thermal energy and dense physical impurities actually physically alter the semiconductor's capabilities. The environment literally manipulates the quantum particles.
Okay, section 3, the wide bandgap revolution. We've spent a good amount of time in the microscopic theory of quantum physics now. Let's start zooming out to macroscopic engineering and see how we actually harness all of this.
Manipulating these microscopic band gaps, calculating effective masses, and tracking those phantom holes, this is exactly what allows engineers to build devices like a MOSFET transistor. And transistors are the fundamental building blocks of all power electronics. By meticulously controlling when and how electrons jump that band gap hurdle, we can switch electrical currents on and off with incredible precision and blazing speed, which is exactly what a power charger does to convert wall AC power into battery DC power. For decades, silicon has been the undisputed king of these transistors. But silicon definitely has its limits, particularly when handling high voltages and high temperatures. And that brings us to an absolutely massive breakthrough: wide bandgap technology, specifically gallium nitride, or GaN for short. GaN has a significantly larger forbidden energy gap than silicon. Finding materials with these wider band gaps is the absolute secret sauce behind the current revolution we're seeing in power electronics. A wider band gap means the material can withstand much higher electric fields before breaking down, and that allows for faster switching and dramatically lower energy losses.
All right, section 4, silicon versus gallium nitride. So how does this new champion actually stack up against the old standard in the real world? Let's transition into a direct showdown between silicon and gallium nitride chargers.
Now, what's really interesting about this slide is the data from rigorous efficiency testing, comparing these technologies across different loads. If you look at the data at a lower power rating of 30 watts, both silicon and gallium nitride chargers perform very similarly. They essentially tie with an impressive average efficiency of around 90%. But look what happens when we demand more power. At 60 watts, silicon plateaus at 90%, but gallium nitride actually pulls ahead to 92%. In the world of power electronics, that divergence at higher power levels is absolutely everything. Now, you might be looking at that and thinking, well, a 2% efficiency bump at 60 watts sounds pretty small, right? But because GaN generates far less waste heat, thanks entirely to that wider band gap, it requires far fewer bulky thermal management components. So the real-world consumer benefit is honestly astonishing. A GaN charger is literally half the size and half the weight of a comparable silicon charger. We are talking about a twofold reduction in volume and weight, coupled with higher power density. That tiny 2% efficiency bump literally translates into that incredibly tiny brick you now carry around in your backpack. And believe me, governments are definitely noticing these quantum improvements. For instance, the EU Commission Regulation 2019/1782 mandates that external power supplies over 49 watts have to have at least an 88% average efficiency. While traditional chargers can usually meet this, gallium nitride consistently overperforms. In fact, GaN is proving to be so exceptionally efficient that policy experts are suggesting regulators might actually need to rewrite the rulebook and tighten efficiency regulations even further. This could effectively force the entire market to adopt this wide bandgap technology just to save energy. Let's move to section 5, global energy impact. This brings us to the ultimate payoff. Let's see how this builds into an almost unimaginable scale when applied globally. I want you to just take a second and let that number sink in. Over 6.2 billion. According to data, that was the number of smartphones actively being used in the world in the year 2021. The vast majority of those devices were being plugged into the wall and charged every single day using older, much less efficient silicon chargers. If we were to take all 6.26 billion of those daily phone chargers and swap out those silicon chargers for gallium nitride ones, the energy savings would be profound. We would save 2.2 terawatt hours of electricity globally. That is a staggering figure. To put that into perspective, that is enough energy to power hundreds of thousands of homes for an entire year, all saved simply by utilizing a material with a slightly wider gap between its energy bands. We started all the way back with the mathematical abstraction of a 1D periodic potential, right? And phantom holes moving through atomic lattices. And we ended up literally saving terawatt hours of global energy. Because the power charger market, that was just the first to experience this penetration of wide bandgap devices. So I leave you with this. If manipulating these invisible quantum hurdles can shrink our everyday chargers and save massive amounts of resources, what other massive global technologies will gallium nitride revolutionize next? Are we talking electric vehicles, renewable energy grids? The future of electronics is literally being rewritten at the atomic level, and it is incredibly exciting. Thank you so much for joining me on this explainer. and keep questioning the physics of the world around you.